in equations, okay? So we're not going to do the whole section. We're only going to do the very first part of it. So go to your 2.13 notes. And up at the top, he's done what he does so well. He's written out, or kind of summarized your properties for you. So we're on our 2.13 notes. We're going to spend a little bit of time on this, and then we're going to do questions, okay? But we got to get this down first. It's easy. It's easy. I'm not going to assign any homework from it. It'll be after Christmas we'll have homework when we finish all of the section. But right now, I want you to go down, just go down to example 1. Solve the following equations, leave your answers in exact form. So what does that mean? Do not type it into your calculator. We're going to leave your answers in exact form. So 4 to the x minus 2 equals 7. How do you think we're going to solve this? What are we going to do? You know this, it's easy.
Add the 2.
We're going to add the 2. So 4 to the x equals 9. If that had been, let's say the numbers had been different, and this said 4 to the x equals 16, then it would be easy, right? But it's not 16, it's 9. So what do I need to do in order to solve for that exponent? Log both sides. Now, I always use log. I'm not sure why. I think that's, I don't know. Could I ln both sides? Yes, it makes no difference. You're going to take some logarithm of both sides. So I'm going to log both sides, or ln, doesn't matter. And then the exponent comes out in front. That's one of the properties we talked about yesterday. That's the most amazing, beautiful thing about logarithms. This becomes a coefficient. And now I can solve for it by simply dividing, right? So now I have solved for x. Could I type that into my calculator? Absolutely, it'd be easy. It says not to. All right, so let's try the next one. 2 to the x plus 3 plus 5 equals 26. So what are we going to do first?
Get rid of the 5.
Get rid of the 5. So 2 to the x plus 3 equals 21. Now, 21 is not a power of 2. If that had been like a 16 or something, it would be okay. But it's not. So I'm going to do what I did a minute ago. Right? And I'm going to log both sides, or ln both sides. Take some logarithm of both sides. The exponent is going to come out as a quantity. Does that make sense to everybody?
Why can we do that?
It's a property of logarithms.
It's just math.
Yeah.
Starting with math.
It's the product property of logarithms. Okay. Now, remember for solving for x, so you have a couple of options. Would one option be to divide by log 2? Would that be one option? Is that legit? Yep. And then, since I'm solving for x, I'm now going to have to subtract 3 from both sides. And that would be my answer.
We need to make the 3 like a logarithm match.
Nope. Nope. You're solving. You're not rewriting it. You're solving it.
Could you, would it be wrong if you like took, if you did the,
If you distributed here,
no, like if you separated the 2x plus 3 and made it 2x times 2 to the third, and then did that 8, and then took the log of 21 over 8?
no, that would be fine.
Okay.
that would be fine, yep. You certainly don't need to do that, but it's correct, it is correct. All right, let's do one more. Move the 3 over, so we have negative 10 equals negative 4 e to the x, okay? So negatives are gonna cancel 5/2. I've been logging, and you can still log, but it might be more convenient to ln this one, because what's gonna happen right here? That's just gonna become x. So your answer is whatever the natural logarithm of 5/2 is. You can get the right answer by logging, it just won't be as fast and as neat.
What's the benefit of using ln instead of like log u?
Well, there's no, I mean, you have to type in log e on your calculator. This won't go away. It would be x log e. So you would have to have the log of 5/2 divided by the log of e. And you would physically have to type that in. Whereas here, all you type is ln 5/2. That won't cancel if it's a log. You're gonna still have the e in the answer. It will be the same answer though. It will be exactly the same. All right, example 2. Now we got some problems with logarithms. So what are you gonna do first here? What will be, we're solving now. Our goal is to come up with an x value. So what will we do first? Subtract. All right, so 2 log base 3 x plus 3 equals 6, okay? Divide, so log base 3 x plus 3 equals 3. Yeah, loop-de-loo, 3 to the third equals x plus 3. 3 to the third, lots of 3's equals x plus 3. So this time I'm actually gonna be able to get a number, right? X is gonna be 24. Right? Try B and C with your partner. They might be that same level of easiness. Let's see. Try B and C. See what you can come up with. Okay. Anybody get 13 for the first one? Perfect. And then for for this one, remember the base of ln is e. So this was e to the fifth. So I got 2 minus e to the fifth. Olivia's nodding. Everybody good with that? All right, 4 more problems. That's it. We're just gonna do this, finish this page, and that's it. Now, example 3. I want everybody listening. When your equation looks like log x equals log 17, you are allowed to say, okay, x equals 17. In other words, you can drop those off and just say x equals 17. But you can't do that until your equation says log equals log. That's when you can drop it. So you can't look at this equation and say, oh, I'll just get rid of the logs. No. It has to say log equals log. So the first thing we have to do is put these guys together. Yep. So these are going to be the log of what? This is one of your properties that we talked about the other day. You're going to put these two together. What's going to be in this parentheses?
3x plus 12.
Bingo. 3x plus 12. Why did you multiply 3 and x plus 4?
Because they're added.
Because the individual logarithms were being added. Now it says log equals log. So now you can drop those logs and just solve like a regular equation. I got 7, but I made a mistake there. That's what you got. All right, so there's 3 more, I believe. Go ahead and try those. Remember, you cannot get rid of the logarithms until you have log equals log. First one come out to be 9/5.
Yeah.
That's what you got? Okay. How far? Did you have the second one done? Did you get what I got? Now, here's something we need to talk about. The original problem for problem C, that one right there, was this. Okay. Equals log. if I put a -4, one of my answers was -4. If I put a -4 in here, that would mean I would be taking the log of -2. Can I take the log of a negative? What's the domain of logarithms? The domain is bigger than 0. Yeah, x has to be bigger than 0. If you tried to type in a calculator log -2, it's not gonna like it. You can't take the logarithm of a negative. So this is an extraneous root. Now what I need to make sure you understand is, it's not extraneous because it's negative. We can have negative answers. The reason it's extraneous is, when I put it back into my problem, I end up trying to take the logarithm of a negative. This becomes negative. That's the problem. So if this had been x plus 12, then -4 would be fine. You see the difference? Yeah, I know we worked over here. Let's say I had that. -4 would be a fine answer. So don't cross them off every time they're negative. Plug it back in and see if this stays positive. That's the key. This has to stay positive. So, what if this had been x minus 6? Then the 5 would be extraneous. Do you see? So, in logarithm land, when you're checking for extraneous roots, plug your answers back in, and these have to stay positive. As long as they stay positive, it's all good.
So can you have two answers for that? Like if they both.
You can have two answers to it. You can have no answers to it. Yeah, it's just like, other kinds of equations. Sometimes you have multiple answers. Yeah. Okay, and then for the last one, this is what I got. Is that what you got? Now this one's different. You don't drop the logarithm here because you don't have one on the other side. So what do we do instead? What we did at the top of the page, we moved the root. So e to the second equals x over 3.
I got the same answer, but like I just made it log e of e squared, and then I did log.
Oh, that's fine. That's fine. Yeah. Okay? All right, so I'm making a little notation here that when we return back together, we will begin on the next page. It has a little bit more complicated stuff. Okay, so I know Gus had a question I want to get to first, and then whatever other questions, you have your study materials. Hopefully, you're finding time to look those over, because you'll have time tomorrow to review, and since I won't be here, you will obviously be working with each other. Whatever you can't get figured out with each other tomorrow, we can go over on Monday.
Flips it over,
What was the problem?
over the wall.
So I'm doing a problem from the homework, the 212 homework, number 7. Oh wait, I gotta see if I even have.
It's about the same.
If I have 2 up here.
That, with this 10, is the same thing as that.
All right, so 212, number 7. All right, so which of the following expressions is equivalent to ln just gonna go ahead and start breaking this apart. So that's a division, and that's a multiplication, so ln 5 plus ln e squared minus ln root x. Would everybody agree with that as like the beginning, anyhow? Not much I can do with ln 5. What's ln e squared? 2. And what does the square root of x mean? X to the 1/2, so minus 1/2 ln x. Alex?
Can you do 5 on?
Okay, wait, is this an answer? Is that an answer choice? Yes, so the answer is A.
I have a question about that problem.
Mm-hmm.
Is ln e squared always 2, or is it just that like in this problem? It's always. Well, I mean, I just wanted to make sure.
So Cole, one day, we talked about, there's a property that says, when the base of the logarithm and the base of the exponent are the same, the answer is the exponent.
You're cool.
So the base of that logarithm is e. The base of the logarithm and the base of the exponent are the same.
Okay.
The answer is
That makes sense.
the exponent. All right. So Alex, what was your question? 2.12,
I wasn't here last week.
number 5. So this looks like something we had in the notes. Imagine that. So we're gonna write log base 8 of x as a vertical dilation of the log base 6 of x. So remember, I'll use the same letter we used in the notes. That can be anything, some variable. What does it mean to be a vertical dilation? It means you multiply your function by something. Okay? So what's that k? Well, that k would be the log base 8 of x over the log base 6 of x. This can be rewritten. Remember how that works? What's that? Gonna equal log x over log 8. And likewise, that one is log x over log 6. That's my k. So can that be simplified? Yeah. How do you divide fractions? You
Flip them and multiply.
keep, change, flip, right? So if I do that,
Keep, change, flip.
I'm gonna end up with the log of 6 over the log of 8. Now, is that a number? Like that I could get on my calculator, point whatever? Sure. So it said, basically, find the number that when you multiply it times this logarithm, you end up with this logarithm. So that would be the log base 8 of x equals that number times the log base 6 of x. So that's your vertical dilation, because that's just like a 5 or something. All right? And what else? And it can be from the reviews too, if you started looking at that.
From homework 210, can you do number 7 and then number 9?
Homework 210. Well, you just kind of have to look at your graph up there. Okay, so your first task in number 5 was to graph the inverse, which would be the logarithmic curve. So the picture that you graphed was y, I'm looking at number 5, would be y equals log base A of x. You now have that graph plotted. So then when it says find log base A of 3, and you're gonna approximate it because your graph probably isn't perfect. We'll talk about how you can do it maybe a little more perfectly, but, so you just look, this now is your x value, so where x is 3, what is your y value approximately on your graph? Mine's a little more than 2, but I guess, yeah, it's in that range. It's around 2. I have like 2.5 or 2.8, something like that. Notice how close the exponential comes to the dash line, so you want your logarithm to come close.
I think the problem was more with the graph than the.
Okay. And then 9 is exactly the same, but you're using the other picture. So now you're letting x be 4. So if x is 4, you're way down there negative 3 point something. So we gotta use our graph. Some of you were like typing stuff in your calculator, River, I don't know what you're doing. Anyway, you need to use your graph. Okay, what else?
You do
212. Number 6. Convert this into a natural log. So basically, then I need to change base. That's what I need to do. So let's look at what we've got. Let's just change that real quick. Let's change that into a natural logarithm, and then we'll just times it by 3. Okay, so how do I change the base on that? This will be ln x over ln 10. Remember, change of base formula works with any base. So it's log that over log that, whatever base you want. So now I'm going to times that by 3. So it's 3 ln x over ln 10. Now, if you're allowed to be using the calculator, can you get a number for 3 divided by ln 10? Yep. And so that's some decimal, let's say, 6.83 or something. Then your answer would be 6.83 ln x. Or you can do it like that, exact. Okay? The same exact thing we were doing over here, Declan, works with any base. Here I use base 10 so that it was convenient and I could type that into my calculator if necessary. But I could have just, instead of saying log x over log 8, I could have said ln x over ln 8. Or I could have said log base 6x over log base 6, 8. I could have used any base I wanted. Okay? So that's all that's happening there. All right? All right, now you got 10 minutes to start working, reviewing, whatever. I'm not assigning any additional homework. You have some of that already to get done, turned in.